Hi guys, in this video we're going to go through a couple of examples involving implicit differentiation. So it's important to quickly recall this formula here. That formula is a way to represent the chain rule algebraically, but what we want to do in this case is we want to rewrite this formula in terms of du dx. So by using a bit of algebra, that's going to become... So with almost all of these questions, the first thing that we're going to have to do is we're going to have to differentiate both sides with respect to x. So on the next line from this point, what we're going to do is we can just find the derivative of this term here with respect to x. That will just become 2x. This term here, we're just going to write as dy on dx. And this term here, we're going to have to do something quite interesting. We're going to have to use the product rule, right? Because this y function here, we can think about that being in terms of x. So that's essentially just some function that's in terms of x. Therefore, we can use the product rule to evaluate that. So when evaluating this first term, we could think about our x as being u and our y as being v, and we can now use the product rule to differentiate that term with respect to x. So I'm going to do that over at the side here. So we know that u is equal to x, we know that v is equal to y. U dash would be just 1 if we're differentiating with respect to x. Now, if we're differentiating v with respect to x, v dash is going to actually end up being whatever the derivative is of that function. So v dash is going to be dy dx, which, if we think about it, that's what we're actually trying to find. So we're looking to find dy dx in this situation. So using the product rule, for the first term, I'm going to get the following. So that's what we're going to get. I've just substituted in u v dash v u dash for the first term. The second term is just going to be written as dy on dx. And then the third term is just going to be 2x. Because that is a term that only is in terms of x, we can differentiate that simply, and that's all going to be equal to 0. So let's get rid of these brackets now on the next line. Now what we're going to do is we're going to start grouping some like terms. So I've noticed that there's two terms here that have a dy dx in them. So I'm going to group those together and I'm going to move everything else onto the other side of the equation. Now I'm going to factorize dy dx out the front. So we're going to have, and then now I'm just going to take x minus 1 over to the other side and divide, and we're going to have our answer. So we could say that the derivative of y with respect to x of this curve is going to be this. From this point, what questions usually want is they might want you to find the gradient of the tangent to the curve at a certain point. So if it was 2 and 1, then we'd go and substitute those values in for x and for y, and then that will give us a gradient of the curve at that coordinate. From that point, once we've found the gradient of a tangent at a particular point, we could also go on to find the equation of the tangent. So the actual equation of the line of the tangent, which would be, of course, in terms of y equals mx plus c. So the first thing that we would have to do is we'd have to find the gradient by substituting some coordinates that were given, x and y. We'd have to substitute those into here to get our m value. And then we could go and substitute this same point in for x and in for y, and then go and solve for c. And that would give us the equation of the tangent to a curve. So that question is probably as basic as it gets for this topic. The next 2 or 3 examples are going to be a little bit more challenging. So for this question here, we're finding the gradient of the tangent at a point for the curve that's on the screen. First thing we're going to do, like we do with all of these questions, is we're going to differentiate both sides with respect to x. The first term here is just going to become 3x squared. The second term, what we're going to have to do here, because we've got y cubed in brackets, we're going to let y cubed equal u. So we could say that this is now du on dx. And at the side here, I'm going to say that u is equal to y cubed. Therefore, du on dy would be equal to 3y squared. And then using the chain rule, we could say that du on dx is going to be du on dy times by dy on dx. This entire thing here is going to substitute for this. So when we're differentiating this third term, we're going to use the product rule, which I'm just going to jump straight to the answer because we did that in the first example. And you'll notice that I also brought the 3 to the front before I did the product rule. Then we're going to just have minus 0 equals 0, which are both going to cancel on the next line. So substituting du on dx, we're going to have this. From this point, I've noticed that all of these terms have a 3 in them, so I can imagine factorizing the 3 and then moving it over to the other side, and it will cancel, so all of those 3's can disappear. That's going to leave us with x squared plus y squared dy on dx plus x times by dy on dx plus y equals 0. We're grouping like terms, so we want to keep all of the terms with dy dx on one side and move everything else over to the other side. Then we're going to factorize dy on dx out the front on the left hand side, which is going to leave y squared plus x inside of the brackets, and then we've got minus y minus x squared on the right hand side. Then we're basically there. We're just going to move the y squared plus x over to the other side and divide. And then it's probably a little bit more conventional too, in this case, to factorize the negative out, and probably more conventional to write the x squared term at the front. Now, for this question, remember, we wanted to find the gradient of the tangent at this particular point. So now we're just going to substitute those coordinates, 2 and negative 1, in for x and y. So once we substitute those in, we get this, and then that's going to simplify too. So on the top, we're just going to have negative 3. On the bottom, we're going to have positive 3. So therefore, the gradient at that particular point is going to be negative 1. So with all of these questions, the main thing that you have to be kind of considering is that there are cases where you'll have to use u substitution. Generally, when you've got a term that you're trying to differentiate, that is y, and you'll sometimes have to use the product rule when you've got a situation like this where you've got x times by y. So with this question, we've got to find the gradient of the curve tan x plus tan y equals 3 when x is equal to pi on 4. So the first thing that I've done here is I've taken the derivative with respect to x of both sides. Now with the second term, I've got tan y in brackets. I'm going to let tan y equal u, and then I'm going to find the derivative of u with respect to y. Since we're dealing with a tan function, we get sec squared y. And then using the chain rule, I could say that du on dx would be equal to du on dy times by dy on dx. And we just worked out what du on dy is. That's sec squared y. With the first term, so tan x, I can just find the derivative of that with respect to x. That's going to be sec squared x. Then I've added on du dx because I substituted tan y for being u. And then I've got the derivative of 3 is just going to be 0. Now what I've done is I've gone and substituted du dx, which is what we worked out on the right hand side of the screen. I've gone and substituted that in for du dx, and that becomes sec squared y times by dy dx. Then I've just rearranged, so I've moved the sec squared x over to the other side, and obviously that becomes a negative. Then it's just a matter of moving sec squared y over to the other side and dividing. Now we have our derivative with respect to x. However, for this question, we needed to find the tangent when x is equal to pi on 4. We're just going to simplify this a little bit. We know that sec x is equal to 1 over cos x. It's a reciprocal trig function. So I could go and rewrite sec squared x over sec squared y as this here. I've got 1 over cos x all over 1 over cos y, and then I've made all of that squared because both the numerator and the denominator were squared, and I've just put the negative at the front. So doing a little bit of simplifying with fractions, I can get to this point here. So for this part, we need to find the tangent of y when x is equal to pi on 4. So I'm going to sub in x equals pi on 4 into my original equation, and then we're going to rearrange and solve for y. So I've got the steps here. We're now at a point where we've got tan y is equal to 2. Now, we can think about that as being tan y is equal to 2 over 1. And the reason for that is because we can now create a bit of a triangle from that situation, right? Since tan theta is opposite over adjacent, we could set up a triangle where we've got the 2 is opposite to y, which is the angle that we're trying to find. The 1 is obviously the adjacent side. And then using Pythagoras' theorem, we can figure out that the hypotenuse would be the square root of 5 in this case. So now, since our derivative function dy and dx involves cos x and cos y, we can use this triangle here to find an expression for cos y. So cos y is equal to the adjacent over the hypotenuse. In this case, it's going to be 1 over the square root of 5. And then now we can go and plug this back into cos y into our function for dy on dx. And at the same time, we're also going to substitute x equals pi on 4. So we know that cos pi on 4 is 1 on the square root of 2 using exact values of trig. So I've gone and done that on the following line. Then once we square both of those, we're going to have two fractions that we're dividing. I've done a little bit of algebra and then some simplifying to eventually end up at saying the derivative of y with respect to x when x is equal to pi on 4 is going to be negative 2 on 5. So that's our final answer. I think the trickiest step within all of this question was the triangle step, like just knowing that you can do something like that in order to generate a value for cos y, which is quite tricky.